Hi everybody and welcome back. We are continuing with example 6 in this video. This is part B. We're still looking at page 44 here. And just to refresh your memory on what the instructions are here, they would like us to find the rank and the nullity of this linear transformation and then to decide whether it's one-to-one and whether it's onto. Okay, so in this case we have a transformation that goes from p2 of r to p2 of r. So we're talking about polynomials here. And our definition of the function is we take a t of p of x is just the second derivative of p of x. Okay, so we're going to approach this problem the same way that we did part A by thinking about what the null space of this transformation is, and what we'll discover is that that's kind of enough together with our theorems to answer all of these questions. Okay, now this function that we've got here is a little bit different than the ones that we've considered up to this point. Okay, so we have to think about what types of polynomials could we plug in that would give us the zero polynomial out. And remember the definition of the function, we're taking the second derivative. So I'll give you one example. If you were to take t of a constant polynomial, for example, okay, if you take the second derivative of 2, you're going to get 0, which means that constant polynomials like 2 are going to be in our null space. Okay, can you think of any other types of polynomials that would be in the null space? Okay, any other things, any other polynomials whose second derivative would be 0? If you think about it a little bit, things like 5x would work. Because what happens if you take the second derivative of 5x? Okay, you take the first derivative and you get 5, and then one more derivative gives you 0. And so 5x is also something that's in our null space. We plugged it in, we got 0 out. If you give this a little bit of thought, you can convince yourself that any linear polynomial is going to be 0. Or I'm sorry, the output of any linear polynomial. So in other words, t of a plus bx for any real number a and b is going to give you 0 because the second derivative of any linear function is 0. Okay, what that means then is that the null space of this transformation just looks like everything that has the form a plus bx. Okay, I'm going to remind you where that came from. These are just polynomials whose second derivative is 0. Okay, and this just happens to be, if you break it down, we can write any linear, any first degree polynomial as a linear combination of just 1 and x. Okay, so that forms a basis for the null space and puts us in a situation where we can answer the questions that they're asking us. All right, so let's start with the nullity. What would the nullity of this linear transformation be? Well, the nullity, again, is just the dimension of the null space. And we can see from the calculations that we did that these two polynomials form a basis for the null space of t. Therefore, the nullity has to be 2, because there are 2 of them. Okay, and then the rank we can get by using the dimension theorem. The dimension theorem tells us that the rank of t is going to be the dimension of the domain, p2 of r, minus the nullity. So dimension theorem, and let's see, what is the dimension of p2 of r? That's actually 3. The nullity we just calculated to be 2, and so we're going to get a rank of 1 for this. Okay, and next is, what about one-to-one and onto? Okay, so is this transformation t one-to-one? Okay, well, that comes down to asking about the null space. Is the null space, does it just contain the 0 vector, or does it contain more than the 0 vector? We can see, okay, from the fact that the nullity of t is 2 and not 0, that the null space contains more than the 0 vector, and therefore this function can't be one-to-one. Okay, so by theorem 2.4, t is not one-to-one. Only way that it could be one-to-one is if the nullity is equal to 0. All right, and then finally, we are kind of in the nice favorable position, again, of having v and w be the same. They have the same dimension, and we know that whenever that's the case, that 1-to-1 and onto are equivalent conditions, so the fact that T is not 1-to-1 means that it's also not onto, okay, by theorem 2.5. T is also not onto. Okay, now we're done with the problem, but I want to just leave you with one word of caution. Remember, this last statement that we made here using theorem 2.5, that only works if V and W have the same dimension. You need to be careful about that. If V and W had different dimensions, then we couldn't have used that logic, okay, that we did using theorem 2.5.